Hey, you made it. This is the last review of the last unit in physics for this year. So this is the unit about forces in motion, which also happens to talk about acceleration. Here are the big ideas. So there's two kinds of forces in a way. There's balanced versus unbalanced forces. So when objects are balanced, they're going to be holding still or moving at a constant velocity. When forces are unbalanced, then there's going to be one force that's overpowering another, and that's going to cause movement. Actually, it's going to cause acceleration. And then there's a bunch of types of forces that we talked about in the recognizing forces assignment with system schemas and all that stuff. So if the forces are balanced, then that means they're of equal strength in opposite directions. So these folks are playing tug of war and nobody's going to move because they're each pulling with the exact same force in opposite directions. For a net force of 0, there's no movement, no unbalanced force there. It's balanced, so it's not going to move. But if the forces acting on an object are unbalanced, then that means that one of the forces has more strength than the others. So if these guys are pulling with 400 newtons to this direction, and these guys are pulling with 300 newtons to this direction, there's an imbalance of force, meaning there's more force going in a leftward direction here. And so there's going to be a movement, an acceleration in that direction, okay? So we can also think about those balanced and unbalanced forces in terms of Newton's laws. So Newton's law of inertia is talking about balanced forces. Inertia means that an object is going to tend to resist a change in motion unless acted upon by an unbalanced force. So when forces are balanced, things are either going to stay still or they're going to move at a constant velocity, okay? But Newton's second law says that when forces are unbalanced, then the amount of acceleration is going to be directly related to the amount of force, meaning more force, more acceleration, and it's going to be inversely related to the amount of mass, meaning that the more mass, the less acceleration. So balanced forces are inertia, Newton's first law. Unbalanced forces are force equals mass times acceleration, which is Newton's second law. Okay, so here are a bunch of different kinds of forces that we can have. You'll remember these from the recognizing forces worksheet and also from system schemas and from free body diagrams. So we've got the force of gravity that pulls all objects towards the center of the earth. We have the normal force that supports objects against the force of gravity. So the normal force is what's holding me up on the ground here as gravity pulls me down. If there was only gravity, I would fall into the earth, but the earth has this supportive force on me, also the normal force. Tension force is felt on both sides of a tight wire or rope or cable or string or leash. I like to think about tension force like you're walking your dog and your dog can feel the tension on that leash and you can also feel it. Then there's the spring force, which is what you feel when you squish or stretch a spring. That spring always wants to go back to its like resting position, coiled just like it likes to be. If you're pushing it, you're going to feel that force on both of your fingers pushing it up. And if you're pulling it, then you're going to feel that force on both of your fingers or hands that is wanting to pull it back in. Then there's friction. Friction is the force that is like that rubbing force. So it's a resistance force. When I'm rubbing two things against each other, that resistance is the force of friction. And things with more mass are going to have more friction. Like you can imagine that a fridge is going to have more friction than a wagon or something like that. Then there's the applied force, and the applied force is just the force that you are applying to an object, whether it's by pushing something, pulling it, pushing down a gas pedal, pulling on a cart, any kind of applied force that's being just added to a situation is an applied force. And then there's air resistance. And air resistance is actually a kind of friction with the air. It's a force of resistance, so whatever direction you're going in, there's going to be some air resistance against you going the opposite direction, just like friction. But obviously with air resistance, that force is, it's air instead of an object. So it's going to be less but still significant, right? As we can see with the parachutist, right? That's air resistance is enough to pull that parachutist back up. Okay, so system schema and free body diagrams. These are ways of showing forces. So system schema are these nice circles that we can see here. And the important things to know with these are that there's going to be a dotted line around the force, or sorry, around the object that is the object of focus. So if I'm thinking about the water bottle that is being pulled across the table, then we have the water bottle is the object of focus. We always are going to have the earth in a system schema because we need to have the force of gravity pulling us down towards the earth. We are always going to have everything that the object is touching, anything that there's forces acting there. So as that water bottle is being pulled across the table, there's a force of gravity pulling it down towards the earth. We have the friction force of it against the floor. We have the normal force of the floor supporting it, holding it up. We have the applied force of your hand actually pulling it. And we have the force of air resistance against that water bottle too. Okay? One thing that this picture does not include that you should remember is that the force of gravity is a non-contact force, meaning if I jump in the air, I don't have to be touching anything and the earth is going to pull me back down. That should be a dashed line. So this should technically be a dotted line and this should be a dashed line. So this is a free body diagram. And a free body diagram is thinking about that one object on its own. What are all the forces that are interacting with it right now? So we show just what direction each of those forces is pushing or pulling in and how much is there. So we've got 10 newtons of normal force, that support force holding this thing up, balanced by 10 newtons of gravity. If this was unbalanced, right, then there'd be an acceleration. Unbalanced forces cause acceleration, but balanced forces just work with inertia. So this thing is going to stay put where it is on an up and down basis. It's not going to sink or rise, but I see that there is 15 newtons of applied force going to the right and 4 newtons of friction force. So that makes me think that there is an acceleration to the right of 11 newtons of force in that direction. Okay? So the net force, we could think about, the net force can be calculated from a free body diagram. And that's going to be, so this adds up to 0 here, and this is going to be 11 newtons of force to the right is the net force. Okay, so system schema, this tells you how to draw it. So we've got these nice dotted or dashed lines here for the non-contact force of gravity. It also works for the non-contact forces of the electric force and the force of magnetism, but we haven't looked at those in this unit. And then you have a dotted line around the object of focus. And each one of those objects is connected by lines that are then labeled with forces. Free body diagrams have a main object, and then the forces that are acting on it in which directions. And you can tell the size of the forces by the size of the arrows. And oftentimes there'll be numbers there to tell you how much force is there, but not always. So, this is going to be a multi-video one, I can tell. Okay, calculating net force and determining motion. So we're going to add and subtract forces and determine motion. So again, if forces are balanced, there's going to be a net force equal to 0 because 100 newtons this way and 100 newtons that way is going to cancel each other out and add up to 0. If the forces are unbalanced, then there's going to be an acceleration in one direction or another, right? There's a net force that is not equal to 0. So if we have a weak force to the right and a strong force to the left, then what I can actually do visually is I can look at how much smaller is that arrow than this one. So I'd be like, this arrow minus that arrow is a net force of about that size to the left in this case. So again, we're subtracting the forces that are going in opposite directions, but if they're going in the same direction, we're going to add them. So, yep, here's net force going in opposite directions with the same amount is a net force of 0. But if we have forces that are going in the same direction, we're going to add them together. So this is an example here. These kids are both pulling with 450 newtons, then there is 900 newtons of force going this way. Another thing we've done with some problems in the past is having like the applied force going one way, like a car accelerating with a certain amount of force in one direction, and then having friction and air resistance coming against it in the opposite direction. You add friction and air resistance together and subtract that from the applied force. So yeah, so this is 500 newtons this way, 450 newtons that way. So there's a net force here of 50 newtons to the left. Okay, and the direction of motion is going to be in the direction of the stronger force. There was a lot in this unit. I'm going to keep going, and I'll start this video as soon as 15 minutes runs up. So relating position, velocity, and acceleration. So this is looking at how do we show this on a graph? What do these different things mean? Position is just where you are in relation to a reference point. So yeah, this teacher starts here and she ends up right there. So that's how far she moved. Velocity is how fast you're going, meaning how far you're traveling in a certain amount of time. And if you have positive velocity, then you're moving in the forward direction, or like on the positive part of the graph. If you have negative velocity, you're moving in a backwards direction, or yeah, in a backwards direction, and that could be, and that's on the negative side of the graph, right? Let's see. Acceleration can be a few different things. It can be speeding up, as you can imagine. It can be slowing down, or it can be changing directions. And it also can be a combination of all of those things. For our purposes, we're going to have just acceleration, just speeding up or slowing down. We don't really talk about changing directions yet much. So here's some descriptions of different kinds of motion. Again, net forces are when the object's forces are all balanced. Constant speed also is a product of balanced forces. If the net force is not zero, you're going to see an acceleration in one direction or another. And how that direction is depends on whether the velocity is positive or negative and whether the acceleration is positive or negative. So if the velocity and the acceleration are zero, there's going to be zero net forces, right? Which doesn't mean there's no forces, it just means that they're all balanced. So positive velocity and positive acceleration are going to be a forward speeding up. Positive velocity and negative acceleration are going to be going forwards but slowing down, moving less and less meters per second. Negative velocity and negative acceleration mean you're going in a backwards direction and getting faster and faster. That negative amount of acceleration, or the negative acceleration, means that you are going more and more meters in a negative direction than you were before. That's why it's a speeding up. And then negative velocity and positive acceleration means that you are going backwards, but you're slowing down because the forces are kind of working against each other. You guys will see some notes about that on your tests that I return to you. Okay, I'm going to stop this video and do these next couple in a second video. See you soon.